Good morning, everyone. I'm Shankar. Today I'll be presenting about my work called Bold. This is work done jointly with my advisor, Professor Michael Swift and Professor Namsung Kim. There are lots of benefits in changing the set of active process in a system. First, energy savings. Most mobile vendors turn off cores during low system utilization. Even in case of servers, techniques like core parking, they allow the threads to be migrated to a single socket, thereby the other socket could be turned off. Second, the other case compared to energy savings is the performance. When there is a surge in the workload, then we might want to add more processing capacity to the system, thereby the increased demand can be processed. Third, power constraints. So future processors will be constrained by power limits, and given the limited power, we cannot use all the resources at full power. So for example, in this case, we have two smaller cores and a single larger core. Both type of cores cannot be used at the same time. So in order to use a particular configuration, we need to either turn on a set of cores or turn off a set of cores. These features are particularly important in modern architectures like disaggregated servers and also in virtualized environments in allowing applications to scale up and down easily. So in disaggregated server, for example, moonshot servers, it's easier to physically add or remove resources. So reconfiguration support could allow for a better resource management. In case of a virtualized setting, virtual machine scaling is possible. For example, IBM uses DL path, that is dynamic logical partitioning technique. Thereby, they can add or remove virtual CPUs to or from a virtual machine. Thus, we can observe that reconfiguration is used across a wide variety and a different computing landscape. So knowing all these benefits, let's see how the reconfiguration support is provided by the operating system. So one of the most widely used OS and open source OS, Linux, supports a mechanism called hot plug. So the hot plug mechanism allows you to logically turn off or turn on cores. Thereby the number of cores visible to the operating system would change. So however, the catch is that hot plug was not designed for the purpose of reconfiguration, though it's being used for that reason today. It was designed primarily as a reliability mechanism in order to remove a faulty core from the system. It's also used for testing purposes to vary the number of cores visible to the operating system. So these are not commonly occurring events. And so the hot plug design did not have speed as one of its primary goal. As a result, the mechanism is slow. It takes around tens to hundreds of milliseconds to complete a reconfiguration event. Millisecond granularity still might seem to be faster, but we'll get a clear context when we compare this with a hardware configuration. So process could move in and out of sleep states in the order of 10 to 100 microseconds. So if we consider the hot plug, it's really the software, that is the operating system implementation, that slows down the entire reconfiguration. So if we can reconfigure faster, then we can reconfigure on a shorter time scale. This can allow us to reconfigure more often to build a high performance or more energy efficient systems. Simply put, faster we make the mechanism, more often we can use it. So the problem statement is, how do we achieve a faster reconfiguration? We built a system called Bold that could perform processor reconfiguration around 20 times much faster than the Linux hot plug mechanism. So this will be the outline for the rest of my talk today. First, I'll give a brief overview on how hot plug works. Then I'll talk about the system that we built, Bold, and finally show some results comparing Bold with the native Linux hot plug. So at a very high level, hot plug consists of two phases. First, it is a subscription phase. So when the operating system boots, kernel subsystems can register for hot plug callbacks. So especially when the subsystem would like to do something when a core gets added or removed from the system. So this is particularly the case if a subsystem would like to make use of per core structures like per core queues. In total, we found in our setting there were around 50 subscriptions from different kernel subsystems in the operating system. So the second phase happens when a hot plug event is triggered. That is when a CPU is added or removed from the system. In this case, hot plug mechanism would send out notification to all the subsystems that registered during the first phase. So during these notifications, subsystem can do different operations like migrating threads, also enabling or disabling watchdog services. So to understand why this contributes to a slow hot plug mechanism, I'll go into a bit of details about how CPU offline and the online mechanisms are handled by hot plug. So first, let's see the offline case. So hot plug sends out various kinds of messages while performing the reconfiguration. In case of offline, it sends out the down prepare, the dying and the dead message, and including the post dead message. So each of them corresponding to before, during, and after the CPU has moved to offline state. So different set of notification gives more flexibility in allowing the subsystems to perform different kind of operations like rescheduling the threads, freeing data structures at appropriate times. So it should be noted here that every message that is sent is being sent to all the 50 subscribers in the system. Next, the stop machine interface, which checks if preemption and interrupts are enabled on all the CPUs in the system, without which offline cannot progress further, and the CPU dying message is sent as part of this phase. And the final important point to note here is that bulk of the hot plug operation is performed by holding a global lock. So this means only one of the reconfiguration event could happen at any point in time. So similar set of notifications are sent while bringing a CPU to the online stage. The differing point here is marked by the asterisk, where startup IPI, that is the interprocessor interrupt, is sent to the newly coming up core, and some of the software initialization happens during that part as well. So similar to the offline case, the global lock is held here, and the main point to note both in the case of offline and online, there are several notification messages that are sent throughout the reconfiguration event, and the global locks prevents multiple reconfiguration events to happen concurrently. So we saw how offline and online events work, but what really contributes to the slowness of the mechanism? So as I mentioned earlier, hot plug is designed for a different purpose. It assumes that the reconfiguration events are uncommon, and so if a CPU state changes from online to offline or vice versa, it assumes that the state change is permanent. So this manifests into three different limitations that contribute to the slowness of hot plug. So the first, hot plug is synchronous in the sense that whenever a notification message is sent, all the callbacks are executed in the critical path. Second, hot plug is pessimistic in the sense that CPU state change does not happen often, and so it clears or initializes all the software structures completely. And finally, hot plug is serial since it's done for the purpose of core failing, and core failing is not a very frequent event. So though these reasons make sense for handling the event of faulty core, the mechanism is still slow and does not expect rapid reconfiguration. So next, I'll talk about the system that we built called Bolt. So Bolt is started off primarily by changing the assumption of the hot plug that the reconfiguration events are going to be frequent. So the CPU can switch back from online on the offline states pretty frequently. So with this assumption, Bolt tackles the limitations of hot plug through the following methods. First, it avoids sending all the notifications, notification handling in the critical path, and try to defer work from the critical path and reducing the latency. Second, it does not take the pessimistic approach by avoiding freeing and initializing structures. Rather, it tries to reuse the software structures. And finally, it exposes the bulk interface to overcome the serial nature of the hot plug. The new interface supports the ability to reconfigure multiple cores, which could be of greater use in a larger multi-core system. So Bolt is built over the current hot plug infrastructure. It still retains the two-phase approach of hot plug, the subscription and the notification phase. The different notification messages are still sent for the registered callbacks. However, Bolt improves on hot plug by classifying all of these notifications into either a critical or a non-critical operation. Critical operations are those that need to be executed immediately for the correctness of the system. For example, migrating threads from an offline CPU. Whereas the non-critical operations can be executed at a later point in time, for example, freeing a memory structure. So the job is to classify all of the 50 different hot plug callbacks into either a critical or a non-critical operation. So to help with this, we came up with different categories of hot plug operations. So most of the categories are displayed here. I'll talk about a few. One, the state migration. So it is to do with moving per CPU states, like the threads present in the run queue or some of the per core software interrupts filed there. So when a CPU is about to be offline, all of these need to be migrated to another active CPU. Second, the thread operations can be considered as dealing with creating or deleting threads or putting the threads into park or the unpark operations over them. So the main point here is that we went through all of the 50 callbacks to classify them into one of these categories. So with this categorization, it becomes much easier to classify, since we have to identify if a category is critical or non-critical. So as mentioned before, critical operations need to be handled immediately. So the categories shown here are classified as critical operations. I'll explain a few cases here. I already went to the state migration. I'll talk about the global bit mask. So there are some global bit masks like CPU online mask and others which are used widely in the Linux system. And most of the system execution depends a lot on the correctness of this mask. So any notification callback that tries to play around with these global mask should be handled immediately. So similarly, there are other categories which I won't be talking about here, but you could refer the paper for further details. So bold leaves these operations unchanged, and they are handled like how they are handled in the hot plug. So that's all the critical operations are handled synchronously in bold. So moving on to the non-critical operations, the categories displayed here are classified as non-critical ones. For example, the notification handlers that are dealing with software structures are handled in two different ways. So the first, rather than freeing the memory, the cleanup is being deferred. Usually, most of the subsystems has a master thread which we modify to handle this cleanup operation at a later point in time. In few cases, system information that are exposed through sysfs, so usually the hot plug mechanism clears up or it reinitializes all these software structures during the callback. But rather, Bolt does not do that. Any access to these files are checked during the file open invocation, and the access is allowed only if the CPU is online. So more details on thread operations again are present in the paper. So moving on, we were able to identify somewhere around 30 out of the 50 callbacks in our system and classify them as non-critical operation. We remove all of these from the critical path by modifying the way handlers work. However, the interfacing with the reconfiguration mechanism, that is the primary hot plug mechanism, is still retained. So the last part of Bolt is the support for bulk interface. So the bulk interface allows for multiple cores to be reconfigured at once. So there are two main features through which the bulk interface works. First, the notion of aggregation. So all the notification messages that are marked here in red are passed as CPU mask in bulk interface. So this allows the callbacks to avoid any redundant execution. So for example, so the blocks marked here can be thought of as a state change that happens when a CPU is removed. So instead of going via multiple state changes sequentially, what bulk interface allows you to do is directly reach the destination state, because all the CPUs that are going to go offline state are passed along a CPU mask to the notification handler. So some of the notification messages, for example, the CPU dying in this case, where the notification messages are handled in parallel on multiple CPUs. So it's primarily the aggregation feature and the parallel execution feature that's being provided by the bulk interface. Similarly, for the case of offline, the few of the messages marked in red use the aggregation feature, and the CPU starting message are handled parallelly on multiple CPUs. So moving on, I'll show some results comparing the Bolt with the native hot plug mechanism. So we use two platforms, one on a x86 machine and ARM, the big little architecture. So all the experiments that I'll be showing, we measured the latency of the reconfiguration event, where the latency starts from the moment the reconfiguration is started until the point where all the messages are sent and handled. So first, let's look at the case of CPU offline. X-axis shows the different systems, and Y-axis shows the time in milliseconds. The numbers marked above the bar is the total latency of that operation. So one of the major latency contributor here is in the down prepare stage where the thread delete operation happens. So another latency contributor is primarily due to the use of RCU lock that has to wait till all the CPUs has to undergo like a context switch operation. So Bolt gets rid of the major overhead in this case, since the thread operations are considered as non-critical and that's not happening in the critical path. It's primarily handled by reusing the threads. And in case of the RCU lock, the Bolt replaces the RCU with a different locking mechanism to reduce the primary critical path latency. So with this, Bolt was able to provide speed up of about 15 to 20x for the offline case, and a similar graph here for the online case. So for the x86, a reschedule event primarily caused the most of the overhead, and for the Exynos system, the thread creation that happens during the when the CPU comes up, that causes a major overhead. So for Bolt, in case of x86, the reordering all the notification messages avoids any waiting delay, and for Exynos, by reusing the threads, all these overheads are removed. I'll quickly go over the performance of the bulk interface. So the x-axis shows the number of cores configured, and y-axis the latency. So the primary point to be noted here is the latency of the hot plug mechanism or even the sequential mechanism kind of scales linearly with the number of cores that we reconfigure. Whereas if you observe the slope of the curve for Bolt bulk interface, it's kind of flat. So the primary reason is even when you configure multiple number of cores, the latency does not climb up or does not climb linearly because of the parallel execution and the aggregation done as part of bulk. So to conclude, so hot plug is used as a reconfiguration mechanism, though it's not designed for that purpose because there's no other better alternative that exists. So Bolt is able to reduce the reconfiguration latency by classifying into critical and non-critical. It also supports the bulk interface, which allows multiple cores to be reconfigured. And the final point to note, though Bolt is built on hot plug, the principles that it employs can be applied to in common to any other reconfiguration mechanism. Thanks, and with that, I'll take any questions.
Hi, Mothi, ETH Zurich. Fine work, and looks like a fairly heroic piece of programming. So I was wondering how much of what you had to do was due to basically just an inherently dealing with distributed state in an operating system and cores coming and going, and how much of it was actually a result of the structure of Linux? If you had a sort of differently structured operating system, what would change? Would some things be easier? Would some things be harder?
So most of these modifications were primarily because Linux tries to have all these per core structures and all these like scalability. So primarily every subsystem in Linux tries to see all the cores in the system. So whenever like a core is added or removed, it kind of like involves a notification to be sent like throughout the Linux. So I would say the 90% or somewhere around like more than 75% of all these latencies are primarily due to the way or the design of Linux.
Okay, thanks very much.
Thanks.
Very interesting work. Thank you. Two questions. One is, for this type of solution, how much kernel work did you need to do, and how hard do you think it would be to get accepted into the main line of Linux?
So one of the problem was, so most of the time the type of question that I get asked, so by deferring the work, when do you really handle such the deferred work item? So right now, like we have done these things based on our understanding, which might be completely different from the actual contributor of the Linux. So having said that, so one of the good thing about this design is that even if you classify any of the non-critical operation as a critical operation, it might increase the latency, but the correctness of the system is still preserved. So the main problem arrives when the other case. So if you wrongly classify a critical as a non-critical, then that's where the problem is. So again, one more last point I want to make. Out of these 50 subscriptions, maybe around like 10 subscriptions were really hard to understand. So, but the others, like close to 40 subscription or the notifications, were really easier to modify. So, I think it's probably like easier to make more changes with the approach that we took, rather than like making like a scheduler related changes or those kind of things.
And my second question is, you've made it tremendously faster. Is it fast enough? Do you think with what you've achieved with Bolt, you can actually use that mechanism for rapid state change to save power?
So this is, I'd say, like this is our first attempt. So even though the latency numbers are 20x better, there are other systems like Processor Proxy and Barrelfish which offer solution close to 10 microseconds, including the software overhead. So I would say there's a long way to go here, but if there are real benefits in using such a fast mechanism, then I'd probably say like there would be a lot of focus in improving the latency more. Thanks.
Hi, just a quick question. Do you have a sense of the 50 or so notifications sent out? What was sort of the time breakdowns of these? Like, if you were to like, how long do these things take? Like, is there like?
So I would say like close to like 20% of these notifications were the major contributor, or 20 or less. Others were like just a notification send, maybe changing a variable or make note of something. So it's mostly like 10 to 20% of these 50 subscriptions like contribute to almost 95% of the entire latency. Thanks.
Let's thank our speaker.
Thank you.